Start then. So my name is Will Oldroyd from NAU, like Bob said, and I am going to talk about the search for Planet X. But first, I'll tell you a little bit more about me. Here's me with my lovely wife, Jamie, and our son, Garrett, who's 4. We love playing board games. I especially enjoy chess. I like hiking as well. This is me at Arches National Park in Utah. I enjoy travel. This is Bern, Switzerland here with a statue of Albert Einstein. I buy a statue of Albert Einstein. He lived in Bern when he made a lot of his discoveries. I also enjoy cooking. This is a delicious burger. And earlier today, I made some nice chicken fajitas. So those are a few of my non-work hobbies, but I also love astronomy. And so I'm really excited to talk to you about Planet X and how we got there. So we'll start so long ago that there's no written records. In ancient times, planets were one of the most important parts of the night sky. And in our day, there's a lot of light pollution. And so if you go outside, especially if you're in a city, then when you look at the sky, it's not nearly as impressive as this. But something not too different from this impressive scene would have been what everyone would see every night before there were streetlights, pretty much. And so the night sky was hugely important to the ancient people. And the planets, which the name planet comes from the Greek term for wanderer. They were the stars that wandered around in the sky. The planets helped them know not just the yearly cycle, not just the seasons, but multi-year cycles. For example, Jupiter's orbit takes 12 years to go around the sun. And so there are several 12-year cycles in many cultures, and Venus takes less than a year to go around the sun, and Venus was very important as well. So moving on from ancient times, back then they had basically 5 known planets. They had Mercury, Venus, Mars, Jupiter, and Saturn, and those were 5 of the main celestial objects, including the moon and the sun. Then if we fast forward to 1610, we get Galileo Galilei. And he wasn't the person who invented the telescope, but he was basically the second person to make a telescope. And he was the first one to do a good job. So he heard about this idea and decided he would try it, rubbed glass together to make lenses and put it together like this. And of course, one of the first things he looks at is the night sky. So he looks at bodies like Jupiter here. And that's when he discovered the moons of Jupiter. And he looked at Venus and discovered that it could be a crescent shape like the moon, even though it was much smaller and not very close to Earth comparatively. He also discovered the ears of Saturn. They were really the rings, but he didn't know what they were, and so he called them ears. So here is some spacecraft images of the 4 biggest moons of Jupiter. Now there's 67 or more that have been discovered, but these are the 4 big ones that you can see with a small telescope. We've got Io, which is like a volcano world, Europa, Ganymede, and Callisto, which are all ice planets, basically, ice moons. And really, this was the first time anything like a planet was discovered in our solar system since as soon as people noticed that there was the night sky, long before any written records. And so that was very, very exciting, and it ushered in this age of modern astronomy in 1610. About 170 years later, we have much bigger telescopes. This is William Herschel and his sister Caroline. They were musicians, and he was a composer. I don't remember which British court they were in, but somewhere their job was to write music and play music And their hobby was to go in the backyard with their very nice telescope that they had for the time, especially, and discover new comets. So they'd go out, and usually William Herschel would be at the telescope, and his sister Caroline would be usually in a room in the house nearby, so that she could have the lamplight without making it so William here lost his night vision. So he would call out observations to her, and she'd write them down. And she also made some observations herself. Anyway, one day they were out looking for new comets, and they discovered what they thought was a new comet. And after some follow-up and looking at it more, it turned out to be the planet Uranus. And so this was huge because it was the first time a new planet was discovered in our solar system. For some reference, this is a picture from the Keck Observatory on Mauna Kea, big volcano in Hawaii. You can see these beautiful rings and the nice sideways angle it's tilted at. Really fun. So because Uranus was discovered, it opened up lots of possibilities that there could be more planets in our solar system. And so from that time forward, people started thinking about planets and there being more planets in the solar system. Then in 1801, just I think 20 years after Herschel discovered Uranus, an Italian astronomer by the name of Giuseppe Piazzi was looking at the night sky, and he discovered a new planet also. But it wasn't Neptune. He discovered what's now a dwarf planet, Ceres. It's also the biggest asteroid in the asteroid belt. And so he published this discovery. It was really exciting. Here's what it looks like up close from the Dawn spacecraft that visited it. It's got these weird salt deposits that are really, really reflective and bright. Very interesting dwarf planet. But Piazzi lost it. Only a few weeks after he first discovered it, it passed behind the sun. So when you're observing, if the sun's here, you can only observe to a certain angle before the asteroid or planet or whatever you're looking at gets lost behind the sun. And so it got lost behind the sun. He watched for it really carefully when it was supposed to come back, but no one could find it when it was supposed to have come back out from behind the sun. And so there was lots of debate. Some people said, oh, it's fake, it's not real. And other people are like, it was probably real, but we have no idea where it was. And so along came this fellow by the name of Carl Friedrich Gauss. And he was a 24-year-old mathematician, what might be considered a graduate student now, probably just out of school, recently finished up his studies, and had lots of enthusiasm. And so he decided he was going to invent the math that was needed to find Ceres, this asteroid, this new planet. And so after cranking out some calculations, he went and predicted where it should be and rediscovered Ceres. And everyone was really excited. It was a huge win because it was the first time that math was used to discover or rediscover anything in the solar system. So he used the calculations from Newton and Kepler, lots of giants that came before him. So along with that thinking, we'll fast forward here another 45 years to these gentlemen here, Leverrier and Adams. And they were both mathematicians and astronomers. So they were looking at Uranus and doing all of this math that Gauss laid the foundation for. So they were doing a bunch of math, figuring out orbits, and looking at Uranus. It wasn't doing what it was supposed to do. It was slightly off in its orbit, and they tried to figure out why. Couldn't see any huge errors in the measurements, and decided that the reason the orbit of Uranus was off was because there was another planet in the solar system. And so Leverrier here told his observer friend, Gaia, who was at the telescope all the time, he said, tonight, go look right here and you're going to find a planet. And he did in less than an hour. And that planet was Neptune. So it was another huge win, not only for observational astronomy, but for mathematical and predictive astronomy, that you could use math to find a planet. So this is the precedence that was set when Percival Lowell came along. Now, Percival Lowell was a wealthy businessman who decided he wanted to be an astronomer, so he moved to Flagstaff and built an observatory with a very, very nice telescope, especially for the time. It's still here up in Flagstaff, really cool. After the pandemic, you should all come up and visit it because it's a great experience. Anyway, Percival Lowell was convinced, he had done the math, he was convinced that there was another planet in our solar system after Neptune. And he called this planet Planet X. And so he hired a farm boy named Clyde Tombaugh to come and use the telescope every night and look for this Planet X. And so 15 years after Percival Lowell made this conjecture that there was another planet, Clyde Tombaugh discovered Pluto. Now, Pluto was not the Planet X that was expected, and it was discovered after Percival Lowell died. So he didn't even get to see his exciting result. But everyone immediately fell in love with Pluto as the 9th planet and how amazing it was. Here is a picture of me at Lowell Observatory. This is the telescope that Clyde Tombaugh used to discover Pluto. And what he would do is he would take this big glass plate that had photographic, it wasn't photographic film, it was a photographic plate. They would take the plate out in the dark and slide it into this back board here of the telescope. And the light would come in through the telescope and hit that plate, and where the stars were, it would sort of expose the chemicals on there to show up, and then he would take the plate after an exposure and he'd take it in and develop it. And then he'd bring out another plate and put it in. And he'd do this night after night after night for years. And he would always come back to the same spot a little while later, because things that are moving in the sky, like planets, will be in different spots a couple days later. So what he did is he used a machine that he helped come up with called a blink comparator. And it was essentially a special microscope with two sides. You put a glass plate in each side, and then you'd be able to scroll across and blink back and forth between the two. So he'd be up in this top left-hand corner and then blink over here, and blink back and blink over here and blink back, and then scroll along a little bit and go back and forth, looking for a tiny little dot like this one that moved just a little bit. So you can see these two stars here in the middle for reference. It's over here, and then it moved from about here to right there. Just a tiny little dot that moved a little bit. And that was Pluto. That was the discovery of Pluto. So he looked for a long time for one dot to move just a little bit. And amazing things came from it, from that hard work. Recently, I guess it's not so recently now, but still recently, New Horizons flew past Pluto, and we got these amazing views of this dynamic world with nitrogen glaciers and really interesting hydrocarbon deposits at the top and really, really dark regions, a very geologically active planet, which it was at the time. And at the time, New Horizons launched to go there. Over here, I think, is an ice volcano. So very exciting. The world fell in love with Pluto, and the idea that there was more stuff out there to discover was perpetuated and encouraged. But it took a really long time after that to continue to find things. 1992, 60 years later, Jane Liu and Dave Jewett made another discovery as they were observing, I believe, also on Mauna Kea in Hawaii. They discovered what's called the Kuiper Belt. And the Kuiper Belt is similar to the asteroid belt. It's a ring of icy asteroids and comets that's beyond Neptune. So here, this yellow orbit here is Pluto, and this white orbit on the outside is Neptune. And all of these are various different asteroids in the Kuiper Belt, or Kuiper Belt objects, as they're often called. And they discovered the first one of these other than Pluto, and many, many, many more followed. And today, I believe there are around 3,300 known Kuiper Belt objects. Then, very quickly after that, another huge new planetary discovery came into the field, and that was done by these Swiss astronomers, Dieter Queloz and Michael Mayor. They discovered the first exoplanets, so planets around other stars. And they did this by measuring the wobble in the star. As the star comes closer to us, it's bluer if it's moving quickly, and if it's going away, it's redder. And they would see the star be bluer and then redder and bluer and then redder, alternating roughly every day. And that was because a giant planet was really, really close to that star and pulling it forward and backward. And they were able to measure it and see that there was a planet a little bit bigger than, or roughly the size of Jupiter, I think, close in to the star. And so that opened up the whole study of exoplanets and exoplanetary science. Now there's over 4,000 exoplanets that have been discovered. You could take an entire PhD just on exoplanets, and lots of people do. So we're not going to cover them more here, but it was another interesting discovery outside of the solar system to deal with planets. So coming back to the solar system, starting in about 2002, so 10 years after the Kuiper Belt had been discovered, these people here, including my advisor at NAU, Chad Trujillo, started discovering more things like Pluto. So not just small asteroids, but Eris, which is the same size as Pluto, Maki, this one's now called Gong Gong, Haumea. They all have interesting names because they're from different mythologies. But they started discovering all of these other Pluto-sized or almost Pluto-sized objects far out in the Kuiper Belt. And that started a big debate. Do we now have 10 planets, 13 planets, 15 planets? How many planets are in our solar system? And so in 2006, the International Astronomical Union voted to make this new class, dwarf planet, to distinguish between the larger planets like the Earth, the terrestrial planets, and these small planet-like objects that weren't quite as big, and there were lots of them kind of clustered in these areas. And so they called them dwarf planets because they didn't quite match, but they're still amazing geologically active worlds that are really cool to study. And I hope we fly to most of these not in the not too distant future. So this is how they voted with these yellow cards and everything. Very interesting. To demote Pluto. So along with that, there were a lot more discoveries. So notice this was not just in 2002, this is 2002 to the present. There are more being found all the time that are in this range. And it's very, very exciting. It's kind of like the Wild West of the solar system. There's always more out there to discover, especially in this dwarf planet class. There are lots and lots of objects that we just haven't found yet. So about 6 years ago, late in 2014, Chad Trujillo, my advisor at NAU, and his collaborator Scott Shepard discovered another one of these dwarf planet-sized objects. It's a very clever name, 2012 VP113. Before any of the objects out there are named, they usually get these license plate numbers from the Minor Planet Center, which is the institute hosted by Harvard that keeps track of where everything in the solar system is. So this is its license plate number. Doesn't have a name yet, but they found that it was really, really far out there, way out in the solar system. And there was only one other thing like it, and that was Sedna right here. So now there were two things like Sedna. Sedna was an oddball because it was so far away. And then this one was so far away as well. So they decided to make a plot, because that's what scientists like to do. And they plotted all of the objects out there that were really far away. So there were lots and lots that were kind of spread out here. This is how far away they are on the x-axis. And on the y-axis is sort of where their orbit points in the sky. It's not the whole story, but that's a part of it. It's where their orbit's pointing. And so they noticed most of them are in every single direction here. But once you cross this line, then they're all sort of clustered between like 60 degrees and negative 60 degrees, roughly. And Sedna and VP113 were really interesting because of their orbits, but I'll show you that later. So they wanted to know why there was that clustering, why they were all lined up there. There are a couple things that can happen with an orbit in the solar system, or an orbit anywhere. Over a long period of time, an orbit will start to precess, which means it kind of turns gradually over time. Think of a top that's spinning, and it's spinning around really fast, but you can notice that the top of the top kind of goes around slower. So it's going around in the orbit a bunch of times, but then the top of the top kind of changes. And that's the same effect that happens here as planets go around. And that's normal. Most things in the solar system do that, especially if they're on these stretched out or elliptical orbits, which there are a lot of further out in the solar system. The further out you get, the more weird stretched out orbits you see. Fun to watch. Okay, so the other option is called libration. And that's where instead of going around and around, it'll go back and forth and be kind of like a pendulum. So here we have the sun here in the middle, and then this is the orbit of planet X, which we'll talk about in a minute here. And this is the orbit of some dwarf planet out there. Now, if you have planet X in there, you can go back and forth like this, instead of the pink orbit going all the way around in a circle. And you can see that here. Trujillo and Shepard did this big simulation where time is right here. This is how long it survived in the solar system, and this is that same angle. And you can see as it goes back and forth that it's constrained to be in that little narrow region instead of all over the whole range of the plot. And so because of that, they said, since we see all of these things stuck here in this little area, it's possible that there is another planet out there in the solar system that's making everything go back and forth and stay in this region when it's far enough away from Neptune. So we look here at the orbits of the most distant things in our solar system, and they do weird things. So if you look, most of them have this really linear area here. They're along one axis, and there's not much to the sides. There are a few of these shorter or medium-ish orbits here that are kind of to the sides, but they're still angled in this general direction. And that is one of the main evidences that there is another planet out there in the solar system. is because all of these orbits are stuck to being back and forth within this region. So they're stuck here. There are also a couple that are directly opposite, and Planet X allows for that too, which is really cool. So this all begs the question, why haven't we found it yet? If we know that there should be a planet out there because of all of these orbits, just like we knew a long time ago that Neptune should be there because of the orbit of Uranus, why can't we find Planet X? And the answer is in how big the solar system is. So we're going to start here with an analogy that's done by one of my favorite YouTubers, Mark Rober. He was a NASA scientist and then quit his job because his YouTube channel was so successful. And now he just makes science YouTube videos. So if we start here on a football field, we can say that the sun is roughly the same size as a soccer ball for scale. So we painted it yellow, we got our soccer ball. We'll see it here on the goal line. And now we're going to lay out the size of the solar system on this football field here. So we can start with Mercury here, about the 10-yard line. It's the size of a fleck of pepper, tiny. And then Venus is at 18 yards away, size of the head of a pin. Earth is about the same size as Venus, so it's also the size of a head of a pin at 26 yards away. And the moon orbits that pretty close, about right here. It's the size of a grain of salt, so pretty hard to even see. Then we get Mars, which is also about the size of a flake of pepper, slightly bigger than Mercury, but it's at the 40-yard line. Also, as a side note, the Perseverance rover is going to be landing on Mars here in a couple weeks on the 18th. So you should all watch that. It's going to be very exciting. Okay, so going on from Mars, we get to Jupiter, but not before we move on to another football field away. So here is Jupiter, the size of a grape, at 135 yards from our soccer ball sun. Now, the asteroid belt is in this region here, and they're all really, really tiny, smaller than a grain of salt. Then, if we want to go on to Saturn, we have to add another football field. And Saturn here is 2.5 football fields away, a slightly smaller grape than Jupiter. The rings are pretty big, though. They'd be out like this far. Okay. I love this analogy. It's really fun. It helps me picture what's going on in the solar system and how far away things really are. To get to Uranus, we had a couple more football fields, and we're about 5 football fields away, the size of a pea. So smaller than Jupiter and Saturn, bigger than the Earth and Venus. Then at 8 football fields away, we get Neptune. Way over here, also the size of a pea. Then that's all of the known planets in our solar system. Pluto would be anywhere from where Neptune is to about that much further away. So about 3 more football fields on average, 11 football fields to get to Pluto, which is smaller than a grain of salt. But to get to Planet X, we have to go a lot more football fields. So it is 309 football fields away from our soccer ball sun, also the size of a pea. That's about 17.5 miles. For scale, that's about where Neptune is if the sun is all the way on the side. So the main reason we haven't found Planet X is because it's so far away that we need to almost know exactly where it is using the best telescopes in the world or off of it to find it. So that is the problem that we're dealing with here. But we still have all of these evidences that it's out there. And the next step that we do is to try to figure out where it is. And that's where my research comes in, and that's where we get really exciting new developments. So if we look here, okay. Here we have a plot of perihelion, which is kind of an interesting metric. It's where an orbit gets closest to the sun. So in those big stretched out orbits, say the sun's right here and it goes all the way out here. The closest spot to the sun in there is its perihelion. And for a circle, that's everywhere. But if you stretch it out, then it's the close spot to the sun. And then this axis here, the eccentricity, is how stretched out our orbit is. So the further up we get on this plot, the more stretched out our orbits are, and the further down, the more circular they are. And the further out we get here is, on our stretched out orbit, really just how far away from the sun we are. So if we look here, these are all of those Kuiper Belt objects that were in that ring picture I showed with the yellow orbit of Pluto. There are a lot of them all over here. But these are the weird ones with those colorful orbits that I showed. And we call those ETNOs, or extreme trans-Neptunian objects, because trans-Neptunian because they're past Neptune, and extreme because they're weird orbits. And then here are the IOCs, or inner Oort cloud objects. There's two different designations we talk about for these really, really distant orbits. This is SEDNA, and here's VP113, that one that Shepard and Trujillo discovered. In the middle of this region here, there's this really big gap. It's about 1 billion miles across, and we don't see anything inside here. We see a couple things down in this area, but we know that those form through a special resonance with Neptune. Neptune works with them just right to move them over here, but nothing comes over here in this really stretched out orbit area. There's just this big gap. And so we want to know, why is there a gap? Can Planet X maybe make this gap? And if Planet X does make this gap, can we use the gap to help us find Planet X? So we use NAU's supercomputer, which is called Monsoon. It has 2,800 plus cores, and each core is like its own computer. Lots of GPUs, which are graphics processing units for doing large computations in multiple dimensions. Has lots of memory and storage, and best of all, it's free for NAU students and faculty to use for research, which is amazing. So I use this all the time as my main tool. Code up a bunch of simulations and run them to see what happens, to try to figure out where in the solar system is Planet X. What I do in these simulations is I stick the sun in there, and I stick some giant planets, Jupiter, Saturn, Uranus, and Neptune in there. I throw in a whole bunch of synthetic objects. So I just come up with a distribution and throw them in so that they look kind of like what we see in the real solar system. And then I go ahead and stick Planet X in there, way out there somewhere on some crazy orbit, and see what happens. I run this for 4.5 billion years of time for these objects to move around. And each little simulation that I run takes anywhere between 1 to 5 days, depending on how many of these different objects I have in there. So it's really, really fun to see what happens when we do this. And we stick Planet X in different places every time, and on different orbits every time, so that we can narrow down and like, okay, that one clearly doesn't work, but maybe this one over here might work. And so we try lots of different options to see. Okay, so when we do simulations, where is it? Okay, it's right here. It's hidden. So without Planet X in our simulations, it will look something like this. So all of these are our Kuiper Belt objects where they start, and this is just Neptune. Every once in a while Neptune gets too close and they start doing weird stuff over here. We'll watch that another time because it's really fun to watch these. So here's where we expect the gap to be over here, and we really just don't get anything anywhere near the gap. But we get lots of these things that look like they belong, and then some interesting wiggly particles over here. Really fun to watch. Just to make it easier to see what was going on there, we'll put it in a heat map. So here in red, these dark reds mean there's lots of particles there all the time. Dark blue means maybe one object went there once in 4.5 billion years, and white means there was never anything there. Now I also put down all of these little green dots are the same as we had a few slides ago that were the black ones, and here are the interesting ones, the ET-NOs and the IOCs, these fun ones that are on either side of the gap. If you look at the heat map part, we don't get any of these, maybe like one or two down here that are questionable if they're even should belong in this group. And we don't get any of these, and we definitely don't see a gap because there's just nothing over here. And so that's begs the question, okay, where do these come from? So we try sticking Planet X in there, like I mentioned. This particular Planet X has 6 Earth masses and is 300 AU away from the Earth, or away from the sun, which an AU is like 26 yards. So that's a lot, really far away. Here we go. So when we put Planet X in there, everyone's off to the races. They don't like hanging out up here, and they fly way out of the screen. So if we look at this again, a lot of them go away at the beginning, but then everything that comes sort of up here gets grabbed by Planet X and pulled across the gap and out past 100 here. And those are the really interesting ones. So at first looking at this, we think, okay, maybe there's not really a gap. No, okay, we can watch it one more time. Maybe there's not really a gap because lots of things cross it. There's stuff in there all the time. And so we're not sure. Okay, maybe there's not really a gap from Planet X, but we see Planet X in our simulations. So we see Planet X in real life. So we want to know, okay, why is Planet X has stuff flying through there, but in real life there is a gap? So we look at our heat map again. Neptune's pulling these objects up, and then Planet X is pulling them out. We can see that there's stuff going out all over the place. And we're not sure what it's actually doing. So we look in here, maybe there's some of a gap because there are areas where there just aren't ever particles, and a lot of it's this darkish blue, but over here's kind of dark blue too. So it's kind of tough to see what's going on. So what we do is we make histograms, which just basically count how many things are in this area. So how many things are in right here, how many are in the gap, and how many are over here is what we want to know. So this green line here is how many are ET-NOs right before the gap. And we see, okay, there's this big peak, there are a bunch right there. And then there's a couple things after the gap, we see those right there. So this axis is just how many things we see. Then we look at our different simulations. So we tried 3 different planets. They have these names. This blue planet here comes up here to make a peak, just like we have over here in the real ones in green. And then we have this big dip, and then it goes back up and then falls off again. So we've got this thing here that looks like a gap. And so we think, maybe there is a gap when we do the simulations. Is that right? Then we can look over here at this yellow one and we see, okay, it comes up here and then goes down and maybe it comes back up a little bit before it goes down again. Maybe that's a gap. Maybe, we'll see. And then we look at this purple one here, and it goes up and then just like the green, comes down in this sort of broad feature, and then there's a definite peak right here before it fades out again. And so we've got, definitely have a gap right there also. And so we say, okay, maybe sometimes Planet X can make a gap if you pick the right Planet X. Awesome, we love that. Why? Why does it do that? So let's go back to our simulation video here. So if Planet X is to make a gap, it's not because there's not anything in the gap. It's because there's fewer things in the gap than over here or over here. So if we look at things back, here you can sort of tell. I'm going to pause it right here. Let's pause it. I can't pause it. There we go. So we'll pause it, and you can see there that as objects appear, they fly across the gap, but then sometimes they come back. And when they come back, they'll come and then turn around again. And sometimes they come all the way up, but sometimes they stay in this area. They come back, turn around, go back, and then they'll come back again. And so sometimes they like to live in this area, whereas objects in the gap are just on their way through. This is like the flyover states here, where you fly over, but you never stop there. But sometimes objects will come, and then they'll come back over here. And they'll come up to here and wait around for a while, and then either get thrown out of the solar system, or they'll come across the gap and then come in and out of this area over here. So that's really fun to look at, and we've plotted it here. On the x-axis, we have how long an object lives in a particular region. So here in red are in the gap region. The blue is the ET nose right before the gap, and the green is after the gap, that one where they come back to. And this is how long on average an object will spend in each region. So we see the green, objects are spending like 90,000 years on average in this green area, whereas it's only like 25,000 years in the red. And so because the gap here is kind of like a flyover region, they just skip past it, and then sometimes they'll come back to stay over here in this area. And a lot of times they like to hang out in this area before flying over. So that is what my research has been focused on for the last while, trying to figure out, okay, why is there even a gap? Does it come from Planet X? And the short answer is yes, the gap is made by Planet X. So the gap is another evidence that Planet X is out there somewhere. So the next step in my research is to figure out, okay, we know that the gap and Planet X are connected. How can we use the gap to help find Planet X? And so I'm going to be running hundreds and thousands more simulations to try to figure out where Planet X is hiding, and we'll use that to narrow in on the spot. Along with that, we use not just these computer simulations to figure out where everything is, but we also use observational surveys. So here is a map of the sky, kind of on this funny projection. Here's the ecliptic, which is kind of like the celestial equator, and here's where the galaxy is, this big red area. All of these circles are places we've looked for Planet X. And I think it's probably within 30 degrees roughly of the blue line, and so that's why there's a lot of looking there. We don't look at the North Pole or the South Pole very much, because it's probably not there. So we look in lots of places. We do that using a few telescopes. So this is Subaru, an 8-meter telescope on Mauna Kea with adaptive optics. The laser's not shooting down aliens or anything. It's for helping the telescope point very, very precisely. And so we use that for a lot of our initial findings. We look in all of these areas, and when we find something that moves, then we have to follow it up to make sure it was really there. And so for that, we use the Magellan telescopes. They're 6.5-meter telescopes. We usually just use one at a time. And they've got this really, really wide field of view. Very nice. They're down in Chile. And we also use the Blanco telescope with the dark energy camera down in Chile. It's a 4-meter. Follow-up, as well as the Lowell Discovery telescope, also a 4-meter in Happy Jack, Arizona, just outside of Flagstaff in the forest. Very, very nice, very fun. So this is one of my favorite parts, when we find a new object, we blink back and forth, just like Clyde Tombaugh did, but with computers, to look for tiny dots that are moving a little bit far out in the solar system. And that is how we look for Planet X. So in summary, the rate of astronomical discoveries are accelerating tremendously, starting in 1610, first time ever, and then at the rate of every 50 to 100 years or so, whereas starting in about the 90s, there's been a huge cascade of discoveries of new things, and especially very, very recently, we've found lots and lots of evidence that there is another planet in our solar system. And the more we study it, the more evidence we find that it's there. And we're getting close. So hopefully soon we're going to find it. Thank you.